Hello everyone, and welcome to this presentation on morphological skeletonization. In this experiment, we explore how iterative erosion and opening operations are used in digital image processing to extract the skeleton or medial axis of a binary object. The goal is to simplify complex shapes into a thin, 1-pixel wide structure, while preserving their overall geometry and connectivity. The main problem we address in this experiment is how to simplify a binary image without losing important shape information. Basic images contain redundant pixels that make shape analysis computationally heavy and less efficient. Therefore, our objective is to use morphological skeletonization to remove these unnecessary pixels while preserving the structure. This experiment applies skeletonization through iterative erosion and opening operations. Our goals are threefold: to gradually shrink binary objects while maintaining structural integrity, to extract the skeleton representation of the object, that is, its medial axis, to overlay the final skeleton on the original image to compare accuracy and connectivity. By doing this, we achieve a clean, simplified representation that maintains the same topology and shape, making it easier for tasks such as pattern recognition, feature extraction, and biometric analysis. Skeletonization is a process that reduces a binary object to its thin, 1-pixel wide skeleton. It removes redundant information from the image while preserving its essential structure. The skeleton represents the core geometry of the object, essentially the central line that runs through the middle of the shape. In digital image processing, this is often referred to as the medial axis. Skeletonization is used in many real-world applications. For example, in pattern recognition, it helps analyze object shapes. In optical character recognition, it enables efficient identification of handwritten or printed text. In medical imaging, it helps extract features such as blood vessel paths or organ structures. This process is achieved through iterative morphological operations, specifically erosion and opening, which progressively thin the object until only its skeleton remains. The mathematical foundation of skeletonization is based on morphological transformations. The skeleton of a binary image, denoted as S of A, is defined as the union of eroded sets minus their corresponding openings. Mathematically, it is expressed as S of A equals union of A minus KB minus open parenthesis A minus KB close parenthesis times B. The process continues until the object completely disappears. Each iteration extracts a layer of the object's boundary, and the union of all these layers forms the final skeleton. This approach guarantees that the final skeleton preserves the original object's connectivity and topology, while simplifying its representation for analysis and pattern matching. Let's now understand the Python implementation of morphological skeletonization using iterative erosion and opening operations, step by step. We begin by importing the necessary libraries. OpenCV is used for image processing, NumPy for array and matrix operations, and matplotlib for displaying the images. Next, we read the input image in grayscale mode using OpenCV's OLED function. We then convert the grayscale image into a binary image, that is, purely black and white. This is done using thresholding, where all pixel values above 127 become white, and all values below that become black. Next, we create a structuring element, using cv2.getStructuringElement. Here, we use a 3x3 cross-shaped kernel, which defines how the morphological operations will interact with the pixels. We then initialize an empty image, called skeleton, to store the final result. It has the same size as the binary image, but starts with all pixel values set to 0. Now comes the main part of the algorithm, the iterative erosion and opening loop. Inside this loop, the image is eroded to shrink the white areas, and then it's opened to remove small noise and separate structures. Let's understand this step by step. Erosion removes one layer of pixels from the boundaries of white regions. Opening then smooths and refines the eroded image. We convert the binary image to color, then mark all skeleton pixels in red. Finally, we display the original image, the skeletonized image, and the overlay using Matplotlib's subplot function. In conclusion, this code demonstrates how iterative erosion and opening can effectively extract the medial axis of a shape, producing a thin, connected skeleton that preserves the object's geometry and structure. The visual results clearly show how the binary object gradually shrinks through iterative erosion and opening until only its thin skeleton remains. The final skeleton accurately represents the medial axis of the shape, while maintaining its connectivity. When overlaid on the original image, the skeleton aligns perfectly with the object's centerline, confirming the success of the morphological skeletonization process and identification. And in network and topology analysis, they help map road networks and biological structures. Thank you for your attention. This experiment on morphological skeletonization demonstrates the power of iterative morphological operations in simplifying binary images while retaining their essential structure. Through erosion and opening, we extracted the medial axis, preserved connectivity, and achieved a compact representation of complex shapes. These results highlight how digital image processing techniques can convert dense visual data into meaningful, analyzable structures, a foundation for modern computer vision and pattern recognition.